right. That looks better. I think. All right. Where are we at? Okay, you guys good? Cool, cool. Seems to be better. Alright. Alright. What up? What's up, y'all? How am I gonna do this? Yeah, I figure we do some math. I'll just let everyone catch up here. How am I gonna do this? Alright, we'll put the chat. Put it there. Where am I gonna do it? Let's see. Be fun. No, that ain't right. Okay. Does that work? Man. Alright, now the chat's up. I think that works. Now, how's that gonna work? What's up, fam? Trying to think how to do this. Anyway, so yeah, I figured we'd do some math on Brilliant. So let me show y'all. This is what I got. And I guess I can read the chat over there. Professor Isam, yeah. I probably don't know much more about differential equations than you guys, trust me. This is more for, well, so like I want to do a video on math. You want me to zoom in? Can you guys read this or no? Or is it too far? I don't know if I can zoom in. This website kind of there, is that better? I'll just kind of, let's go like this. Cool. Yeah, we'll just let everyone come through and then we'll talk a bit more. Oh, you can read it now. So yeah, I can read that there, and then I'll. Yeah, that works. Yeah, I think I kind of agree with that. Like, so yeah, the whole. So I'm planning my next video to be about math and how math is used in engineering, and I like this is really for myself to try and learn better, and I figured I'd kind of do some with you guys because yeah, you don't necessarily you probably won't see math in your career. The way that it all kind of works is the computers do all the math, right? So you basically give the computers these differential equations or partial differential equations, and then they solve them. But what exactly does that mean is kind of what I want to know, and then I can kind of relate that to you guys. And so of course, I need a little crash course in differential equations. You know what I'm saying? Yeah, I guess I can. Like what I'll do is I don't like to keep my live streams public. So what I'll do is I'll keep them. I think it's unlisted. And that way, anyone who has the link can watch them. So I'll make like a folder in the Discord for live streams. I think I'll do that, and then you guys can check him out. Okay. Oh yes. All right, cool. All right. Okay, where was I? So I've done a little bit. So, oh yeah, I'm not on the right right view here. Okay. So yeah, I found this site from I got this from Zach Starr actually. I watched one of his videos, and I'll put some music on. And he talked about, yeah, he had a really good video on differential equations. You guys should check it out. But what's up, Lewis? How deep are we going? I'm not sure. Like I'm just kind of gonna start. Like I spent probably the last day just going through these, and maybe we'll kind of review one with you guys, and then I'll continue off where I was. So have you guys all taken differential equations? Let me know where you guys' level's at. Because I can give like a brief rundown. And actually I'll benefit from this as well. Okay, so you guys are like at least second year, most of you. Second and third year. Yeah, so I think differential equations you take in your second year, and then you take a third year math course, and then you also take further on you start to learn about numerical methods. So like all this stuff. By the way, guys, feel free to donate too. That's how you can kind of support the stream. But I've been wanting to relearn some of this because, like I said, we don't really use math much at our work. But when you do a simulation, that's where the math comes into play. Now it's usually kind of programmed in there, so you don't really have to do much. But you kind of want to understand how these softwares are solving for flow around a wing or pressure loss or like whatever, right? So that's kind of what I think you guys will get out of this. You can stick around if you're electrical, bro. You guys take math as well. I take AP in high school. Advanced physics. No, I didn't. All right. So yeah, why don't we go through? All right. So basically, differential equation. It's an equation that relates a function and its derivatives, right? And they're used a lot. You just don't really recognize, like, because schools do a pretty bad job of showing you how these things are applied. So that's kind of the idea. So here's like an example, right? Is you got someone, let's say, parachuting down, right? Or this could be like coming down from space, right? And you have to figure out the trajectory and the speed that your terminal velocity is going to be once you touch down, which will help you design the size of the chute and whatnot. So if you want to figure out, let's say, how your velocity changes with respect to time, that would be like an example of a differential equation. Where am I? No, I want to go back to this guy. Let's start here. right. Yeah. Okay. Well, I guess we've got all the answers already. But okay, we'll just run through. So you guys are familiar with the drag equation. So the drag equation is 1/2 rho v squared a, right? Essentially proportional to the drag force proportional to your density and your velocity squared and your area. And can I continue? I'm just gonna forward some things here to get to some. All right, so this kind of explains how these equations were kind of solved, like, because initially, I'm probably hundreds of years ago, and when we didn't have these, like, how did we come up with these equations, right? And the way a lot of it was done was through experiments. And then you can also do some unit analysis to figure out what's what. Sorry, I'm just skipping to some of the more interesting parts here. Yeah, so drag force proportional to the density of your fluid times the area times the velocity squared. So that obviously pops up in aircrafts and whatnot when you're trying to figure out drag and lift and all that stuff. Where are the D's that came in here? Yeah, okay, so here's an idea of how like where a differential equation will come into play, right? So if you imagine that you're falling. Where was that free body diagram? Right? Imagine that you're falling. So you're being pulled down by gravity. It's the force of gravity, which is mg. And then you're being pulled up. You've got an opposing force, which is your drag force, and you sum those up, and you get your total force, right? So F equals ma is equal to Fg minus Fd, right? We'll write things down, but basically, you guys can read it. So yeah, I've already kind of like solved these, but this is an example of a differential equation. You might not even think like it's a differential equation, but it is. So ma, which is just dv over dt, is equal to mg times mg minus your drag force. So you see you've got the velocity here, and you've got the derivative here. So this itself is a differential equation. That's an example, and basically you're trying to solve for v. So you're trying to solve for the velocity. And I don't know, maybe do you guys want to go like yeah. So, all right. So then what they do here. So, terminal velocity. So you guys know about terminal velocity? Terminal velocity is eventually you reach let's say you're free falling, and this is used when you're coming back to Earth, from let's say space. You want to achieve a certain terminal velocity so that you don't just get destroyed when you land, right? So that tells you how big you want to size your chute. And the terminal velocity, you find it by basically, like, you reach a point where you're no longer accelerating. Yeah. Nobody asked me to do this, bro. I was doing it anyway. I spent yesterday doing this. I'm like, what? Fuck, I might as well stream it. But yeah, we'll do. Like, I'm thinking we'll start doing a bunch of these. Like as I learn a little bit more Python and stuff, you guys will kind of take you guys through that. It's not really a lecture, bro. This is just, I don't know what it is. Anyway, Yeah, so terminal velocity, what you do is like, okay, you guys know you're free fall. Eventually, you reach a point where you're no longer speeding up anymore, right? So what happens there? What happens is that this acceleration term goes to zero. It means you're no longer accelerating. So you have zero on the right side. That would and this way you can solve for UV. You basically solve for your terminal velocity, and your terminal velocity ends up being this formula. Okay, I'm kind of going through this quickly, and if you guys wanted me to go through it more, just let me know. But basically, that's an example. This is an example of a differential, like an application of a differential equation. Okay, because I always didn't like during school. Um, it's like, oh, how is this stuff really used, right? Yeah. So that's kind of the purpose of this. How can you work in NASA? I don't know. Apply there. All right. Okay, where were we here? Yeah. Okay. Take some questions here and whatnot. Okay, that's all good. Did I have special math class? No. No, I did not. Farhan, you missed my exposing videos. Yeah, I've sort of went away from that. I'm not really into I'm not really in this for any sort of clout or drama. I kind of just I want to improve my skills as an engineer, and I want to relate. I want to relate those to you guys and spend less time exposing and whatnot. And maybe I'll do like some in the future, but definitely not as like personal, if you know what I mean. All right. So you guys might need to help me out with some DEs. Okay. So here's another example, I suppose. This is, I guess, how a DE is used in biology. Vessels are spherical containers, small radii. They're being dragged through the blah, blah, blah. No motors. We're going to build a very simple vessel motion using the model using differential equation, drag force due to the environment of the cell. First, I have to find the drag force law. So let's step 2. We kind of did that already, but maybe it's a little bit different. Viscosity measures the stickiness of a fluid. Honey is a viscosity units M over T. Use dimensional analysis to UNFD. What other quantities besides viscosity? So viscosity, it's interesting. Like the drag force formula doesn't take into account viscosity. I think except for very very low Reynolds numbers. This is not an ad. This is not an ad. I just figured I'd do this. I don't know. I could do a MATLAB video if I knew MATLAB. I'll get there. Yeah, I'll get there. So what other quantities besides viscosity can contribute to the drag force in the vessel? Can you guys answer that? We kind of went over what the drag force is a function of. So basically, you've got like, oh shit. All right, cool. I really need a bigger desk. So you've got like some flow, right? And this is air, which has a density. And what are they using for viscosity? This. Some V. Right. So these are the so your drag force, some function of rho and V, and viscosity, and we'll call this our radius. And that's probably it. Yeah, the velocity, r, density, what are the quantities? The drag, not a function of g, not a function of d. Easy peasy. To cook up a force law, we have to relate the set of physical quantities and v through their units. I haven't done dimensionless. I briefly remember dimensionless or like unit analysis. It's kind of straightforward. It's like, all right, you've got, you know that your CD is a pure number. Okay, so they want us to come up with a formula. Okay, so forget about density. I guess they're not using density here. There are the physical quantities, F, viscosity, radius, and velocity. So try to figure out a formula for drag force. So basically drag force, what they're doing is they're going like this. A is equal to viscosity times B, RC, VD. You got to find out what these exponents are. And the way that they do this is, so your F, the units are kilograms times a meter per second squared. Yeah, that's right. To some exponent. And then the viscosity units are M over LT. It's kind of fun. Over LT to some power. Radius is in meters or length. C, and then speed is length over time. And that's to the D. So dimensionless. So basically, what are all these exponents? So if you look at the formulas, B times C times D has to equal A, right? Or is it plus? No, it's plus, I think. Squared and squared. Yeah, you add. Because you're multiplying, you're adding, you add the exponents. It's not my first time learning. It's been 10 freaking years since I've learned these. So it's a bit of a refresher. So you guys should try and figure out how to solve this too. Okay, so the way I'm just gonna do is your A. Yeah, there's a bunch of equations here. Okay, so your A and B have to be the same, right? Because your M here and your M here, there's only one. So A equals B. Well, A is just gonna be 1, right? Because your force, like you're not gonna give an exponent to your force. B equals 1 then. If A equals 1, then B equals 1 because there's only, like, you have to match your M's. And then if your B is 1, then your D also has to be 1 because here there's 2 T's, and then you have 1 T, and then you need another one. So your D is also 1, which is interesting. It's interesting. It's not a function of velocity squared. And then your L, therefore, now you just, yeah, so now you've got, so you got an L here. So 1 is equal to 1 and then minus 1. So this needs to be 1. So let's see what we get. So I'm saying here that force is proportional to the viscosity and the radius and the velocity. Because that's how these That's how these units would balance, right? You got 1m, you got 2 t's on both sides. You got 1L because there's 2 on the top, 1 on the bottom, so there's 1 and there's 1 on the top here, and then there's... That's it. Let's see what we get. So the answer would be this one here. Yes. Yes. I mess it up, eh? See that? Oh, you guys can't see. Okay, I'll put this here. Okay. Where should I put this in the middle? Let's have it in the center. Anyways. What I want to solve, I don't really know. I'm just going through this lesson. So we're yeah, let's just keep going. All right. If the motor supplies a constant forward force on the vessel, which also experiences a drag force, what differential equation best captures the velocity? Okay, so we kind of saw this already. I want you guys to answer this. So what he's saying is you've got a vessel or vesicle. What exactly is a vesicle? Okay, so this is some like biology stuff. So what he's saying is basically you've got Okay, got a cell and it's being pushed, right? So you got some force acting on this guy. It's also being resisted. Okay, there's some, you got blood in here, right? Let's say this is an artery. Okay, we'll call it the drag force. So the motor supplies a constant forward force on the vessel. What's the differential equation which best captures the velocity? Can you guys answer this? So you've got some force. Let's call this okay, they call this the motor force. So you got motor force minus drag force gives you your total force, right? So let's rewrite this on this side. So F equals this. Okay, so what is F? F is just MA, right? Fm minus drag force, which they give here, and we derived already. So it's CD, this is the drag coefficient, velocity, R, V. Okay, how do we rewrite this? What do we rewrite? What can we rewrite A for in terms of V? Let you guys answer. Correct. Easy one, right? dV over dt. This thing. So that's it. That's all they want to do. Plus? Nah, it's negative. Okay, got that one right. I'll just leave this here. It's getting somewhere. It's getting somewhere. Okay, now do you guys know how you'd solve for the velocity? Like so the whole purpose of doing these exercises is to, well, it's for me to learn. But the whole purpose is to solve for the variable that is like whatever the variable is. In this case, it's the velocity. That's in the differential equations, right? So how do you solve for v, right? Yeah, like how do you solve for velocity as a function? So what you'd end up doing is you would, well, let's just go through it because I'm not necessarily qualified to give the lesson. But yeah, that's the whole purpose is to isolate v and then probably integrate and solve for it. Okay. Convenient step towards solving the DE is to non-dimensionalize was this a process you guys have learned, non-dimensionalizing? I don't really remember it. I know what it means. I don't remember. I don't remember doing it. How many people got watching? Cool. You guys feel free to donate. Support the stream. All right. So what are you guys saying? Integrated factor rearranges the thing, the direct term equals fmc divided by cn divided by dv dt. Yeah, I don't remember, to be honest. Anyway, let's just go through how they do it, because yeah, I'm kind of all right. So non-dimensionalize. Okay, so a times y to the x so a times, let's just write out what they've a times y. God damn it, I really need a bigger desk. Can't see behind my camera stand. V to the t, and then bx equals t. Okay. What's the purpose of this? What option corresponds to the non-dimensionalized version of the Vessel equation above? So yeah, this is anyway. Let's go through this mess. So basically, they're saying substitute anywhere you see t, substitute b, x, anywhere you say v, substitute a and y. So that would, once you plug it into the equation, you get dv, which is a times y x over dt, which is bx. Just stay with me, guys, and we'll get this. Will get somewhere. R v, which is a times y to the x. So what ends up happening here, I think, is you end up getting, because these are a and b are constants, so you're able to take them out of the differential here, and you get dy over dx. Okay. I don't really see what the point of it is, but oh, they want us to keep going. Non-dimensionalized, and then using them to eliminate all physical constants. Okay. Build my own desk? Yeah, maybe. Okay, so what they want us to do is rewrite it in terms of this where you got okay, I see. So they want in terms of dy dx equals 1 minus y. Interesting that this is an absolute. This velocity is absolute. All right, so let's make sure this is absolute. How often do you use DEs at work? Yeah, so not often. Like, you won't. Okay, so the math that you learn is basically all going to be in school. You're probably not going to see any math in your career. The reason that I want to relearn it, like okay, what ends up happening is when you run a simulation, the simulation. So let's say you're doing a CFD analysis, right? The CFD, the software, it calculates, it does all the calculation based on the Navier-Stokes equations. So you give it the equations and it solves for it, right? So the computers basically, they do all the work. Now, personally, I like to learn how things work. I don't really, because you can run your simulations and just take the solutions for what they are. You really don't want to do that. I want to know what exactly the hell it's doing because I really don't understand. So yeah, that's kind of the purpose of this. So you don't have to know. Like you obviously you need to understand in your school. You have to pass these courses, but I don't know. I think it's a good idea. Farhad, man, appreciate it, bro. Appreciate it. Thank you for the $10, and I hope I didn't. Hope you didn't spend all your birthday money on me. But no, thanks, brother. Really appreciate it. Okay, so yeah, that kind of answers the question here. Okay, so we need to remove some of these constants. So we can take a out and we can take b out. So you end up getting m a over b, and we don't know what a and b are yet. I think we'll get there. Times dy over dx is equal to f naught. Remember, f naught is a constant. Minus minus 0 a y. Let's call this y. And then they want us to, so we want to get rid of this. Okay, so that kind of makes sense. So we'll drag this to the, I'm running out of room here. Shucks. Okay. So I'll take this up here. You guys can all see, right? Clear? So we want to keep y prime isolated on the left side, so we're going to divide by the constant here. So we get dy dx is equal to f naught divided by ma over b. Subtract CNRA times y divided by ma over b. And then we can rewrite this. We can take this. We can divide this guy out because okay. So we want it to look like this, where we've got 1 plus whatever. I don't know where the constants go here. I'm not sure. Like, how does this constant? Okay. So like, what you can do, you can take this first term here out. No, that doesn't work. What option corresponds? So maybe A is... this is a little bit confusing. I'll call this AD. This is a different A. I might just look at the solution. Unless you assume that MA over B is equal to F, and then in which case this becomes 1, and then maybe that's how you do it. And then this becomes 1? I'm not sure. I'm just going to look at the solution. It should be a minus here. I still think it should be a minus. There's a minus term. Okay. I'm just curious here what they did. Right, so D, so they divided M. So dy dx, BA, yeah, we got that far. Okay, so they set the constants so that, yeah, it's just it is a general form, and what they do is they set the constants so that you get this, whatever. Okay, we get it. Challenge problem. Let's assume 0. Okay, let's go ahead and erase all this. All right. Let's assume that y of 0 is greater than 0. Okay, so let's assume that y initial is between 0 and 1, meaning the vesicle's already moving in the direction of the motor motion when we start to model it. Since y prime is 1 minus y is separable, we separate and then integrate. Oh man, I don't remember this stuff. You didn't understand at all? Aren't you guys this should be like fresh in your guys' mind. I don't understand. I kind of understand. I don't really remember. Like, do you guys familiar with separable equations? dy over dx is we separate and then integrate. Figure out what function f should be, what function g should be, and then find an implicit relationship. Function f should be. To arrange the function before you differentiate. Okay, so you guys tell me what would be... Yeah, so how would you solve this? So this is how you'd solve it? Like, okay. Okay. So right now we got dy over dx is equal to 1 minus... Okay, and they want us to rewrite this in terms of f of g of x over f of x, yeah? So can I just say g of x is 1 minus y and f of x is 1? Figure out what function f should be, what function g should be, then find an implicit relationship. Matthew, g of x dx is equal to fy dy and integrate. Oh, this is y. Fuck me, I don't know what's going on. This is y. Fy dy. Oh, I see. Okay, yeah, okay. Okay, yeah. You want to separate the variables. And just cross multiply. Yeah. Take 1 minus mod y to the denominator. So you're saying that we want to No, I don't know what's going on. Do we bring the fy do we bring it up there? No, what am I talking about? No, I'm thinking the dy. dy over 1 minus y is equal to dx. Let's see. Okay, so dy equal dx. Is that what you're saying? So how did that work? Okay, that's weird. It's good, right? Okay, so you end up getting this integral becomes ln. Is it negative ln? I'm not sure what you do with the absolute here. But let's just say this for now, and this just becomes x, and then you add the constant. So is this? I don't know. Let's look at the answers. Oh, Christ. Okay, hold on. I see. Let's undo this. Okay, because up here you got y, and then you got y naught. So you get a negative 1 minus y minus ln of 1 minus y naught. Yeah. And then so that becomes So you just take the ratio, but it's negative, so you can flip it. So the y naught will be on the top. So you don't need a negative. So you get y naught on the top, 1 minus y naught over 1 minus y. Hope that's one of the options. And then equal to x plus a constant. But anyway, so that would be this guy. Nice. Now that we have it, let's solve the implicit relationship between y and x. So we can write y explicitly as a function of x. Shit. So ln 1 minus y naught. So we want to write y in terms of x. So to deal with the absolute signs, remember that y is always positive and less than 1. Y is always positive and less than 1 since y naught. Okay, so y naught is kind of fun. Y naught is between 0 and 1 was defined before, which means that this term here, this top term is always going to be greater than 1 or greater than 0, meaning y is always positive and less than 1. To deal with the absolute value signs, remember that y is always positive and less than 1. How do we get rid of the absolute sign, boys? Yeah, I know. I know like how to get rid of the natural log, but the absolute. So y naught is always okay. So this term here, this top term is always greater than 0, and since y is not negative. Since y is also greater than 0, that means that this term is 0. Or this term is always greater than 0, so we can eliminate it. Okay, that makes sense. So whatever. We don't have to rewrite it. We'll just erase these. Okay. So we isolate for y, we raise this to the e. So yeah, you did the power of this, so we end up just getting y minus 1 naught minus y is equal to e to the x, right? This is first order. What is this first order equation? Yeah, this is a first order. Because there's only the first derivative. Okay, is that right so far? And then we can swap these so we get We get 1 minus y naught e to the negative x is equal to 1 minus y. And then we get, so y is equal to 1 subtract 1 minus y naught. Does that look about right? Let's see. 1 minus y and 1 minus e to the minus x. Send it! All right. Yeah, Thanks, guys. You guys get that one there. So, the solution y, whatever, is dimensionless. Right, because we made it dimensionless. All right. We can restore the physical units by remembering that v is equal to the terminal velocity. Okay, so this was derived in the last lesson. Anyway, just take these for what they are. V is the terminal velocity times y, and then you have one for t here. Resulting in v is v terminal minus v naught. Okay. Velocity for any constant force, therefore, will also vary. The velocity for any constant force, therefore, will also vary as a function of time, except for one special initial condition. What is that condition? The velocity for any... Here, I'll give you guys the answers, and you can guess. The velocity for any constant force, therefore, will vary as a function of time, except for one special initial condition. I guess when it's already at terminal velocity, right? Yeah, that's kind of intuitive. And the way you'd solve that, or you'd figure that out, is you just plug in v term for your v naught. And this ends up becoming 0. So your v is just your v terminal. Boom. Is differential equations practical in my current job? Yeah. So now it's not really my area, but there are engineers at my company that do. Like, I see them all the time writing down differential equations. Yeah, because based on like the simulation package you're using, you might, like, most of the time, if you have like a quality simulation package like ANSYS or like COMSOL, these packages are already programmed, right? So you really don't need to do any coding. You don't need to look at any source code. Some of them, like OpenFOAM, you probably do. So yeah, there are engineers, like maybe one or two that I see them looking at DEs, probably to like verify that what they're doing is right. Calc 3, what was Calc 3 again? What did we learn at Calc 3? What do you guys learn at Calc 3? I was trying to remember this the other day. But I forget what I was getting at. Yeah. They're also applicable for trajectory equations. So, flight trajectory, right? Finding the velocity or the acceleration and the distance at different points along a flight path, that's where also differential equations come into play. Sometimes we will do like figure out the handwritten equations and kind of solve it for that. So yeah, it's something I'm still like I'm kind of learning. Yeah. Multivariable calculus. Okay. Yeah. So it's like, you take it. I think you take it along with DEs. Yeah, I don't remember much about. Okay, I get it. Gradients, curls, partials. Yeah. I've been watching a lot of. You guys probably watched 3 Blue, 1 Brown. Sure. Yeah. I was just watching one on Divergence. Yeah. Yeah, because it's really nice when you learn how these are all applied, right? When you take it in school and your professor's like, do you guys know how any of this is applied in the real world? Because you probably don't know in your classes. Like, they probably don't tell you, and that can be kind of annoying. Okay, let's finish this lesson off, and then we'll just. By starting the vessel, terminal velocity remains a terminal velocity. There's no other way for blah, blah, blah. Looking at things from a different perspective. Yeah, I mean, this kind of makes sense. So maybe a better one to do is the heat equation. We looked at the heat equation. It seemed a little bit more applicable. I don't know if this is too abstract for you guys, but it's just, yeah, whatever. Now that we have V, now we have the velocity function. We can calculate interesting things like the energy delivered to the vessel over a period of time. This is where integration come into play. Integral of force times velocity times FVT is energy, is work. Yeah, because FD is work and D is VT. Interesting. All right. So what is the calculate W is short for work. Find the total work of the vessel since it starts from rest. Oh, I don't remember what the formula is for. Well, you could probably think of this like intuitively, right? So work has the same units as energy, and whenever you're talking about energy, these are all obviously kinetic energies. So it would either be mv squared or mv squared over 2. Yeah, probably mv squared over 2 since that's kinetic energy. Anyway. Several equations arise in many physical... Oh, we got 100%, boys and girls. Let's give it up. Several equations arise in many physical applications, not the least of which are motions involving a direct force. Rescaling, we're left with a differential, blah, 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 blah. All right. What do you guys... So, like, yeah, my next video is going to be on math. What are some questions that you guys have? So basically, what I want to talk about in the video is how math is used in engineering, right? Now I've already said that, like I'll just sum it up here. You probably won't use math in your career. It's not 100%, but from my experience and from talking to other engineers, it's something you probably won't see, but math is used. It's used in so many different applications. You just don't see it, right? Because it's all done by computers. So I think it's important to know how these things kind of work. And that's when it really becomes interesting, is like, how do you apply? And that was just like an example, I guess. It was kind of I wouldn't say it's abstract, but it's, it's an example of how it's, like how it would be used, right? One example. You guys can look up let's see. Yeah, the heat equation is another, or Newton's law of cooling, not the heat equation. Newton's law of cooling is another one. But yeah, they're used a lot. Anyway, what questions do you guys want to see? Or what questions do you guys have for the video? Because I'm probably going to film tomorrow. And yeah. Yeah, I speak a little Arabic. Plenty of algebra. The big picture behind ODEs, yeah. That's going to be probably the main goal of the video. Yeah, I've got a lot of research to do. Yeah, FEA is used. We use a lot of CFD. Eventually we will be using FEA when you start to do analysis on the vehicle body. But yeah, definitely will be used. CFD, like you at most jobs you're going to use some simulations, right? Now I don't do it because I'm like they're you usually give it to the engineers who have who are already experienced in it. So yeah, this is stuff I'm trying to learn on my own time. Going to college next year as an engineering major and want to learn Python over the summer. The best way to learn it. So I'm a beginner myself. So I did a tutorial, just a YouTube tutorial. This programming with the Mosh. She's really good. And and now I'm just learning through work. So we have, we've got Python programmed, and that's how I'm doing it. You can, like the guys at my work, a couple of them took boot camps, so that might be a good idea too. Take a coding boot camp. Yeah, because you can only get so far with YouTube tutorials, and then it's like, all right, what do I do now, right? So, so I'd be coding thermodynamic simulation program that's pure math. I don't know if I want to mention what the program is called, but we've got this package that's built in Python, and it's already got. How does it work? It's already got all these modules in them, and so within there, how does this work? Basically, we're not explicitly doing math because all that stuff is it's already been programmed. So where the coding comes in, just to sum it up, no, there's not. We're not doing math explicitly. The math is already sort of programmed in there. That's as best I can answer. How's my student life? Come on, Brian. I've made videos on it. You can look at my grades. It's my highest viewed video. My grades weren't that good, but yeah, student life was all right. I mean, it's a lot of work. I wasn't able to take 6 courses a term, but some people can, and they can balance it. So it's all about discipline, really. How much learning do I have to do on my own time? I choose to do. I like I'm telling you guys. I mean, I'm learning differential equations. I'm learning Python. I probably spend 3 or 4 hours a week. It's good. It's good to keep up, right? It's good. It's because, I mean, you don't always have time to learn these things at work. Although we do get paid to learn, there's still jobs to be done and whatnot. So you don't have to, but you kind of want to if you want to do the fun stuff. All right, we'll take a few more questions and then we'll bounce. Is my job more on the design side? I mean, we do everything, bro. Like we design and then we build and then we test. So it's kind of nice like that. But yeah, I guess you'd call it a design job. For aerospace master's degree, would it be better to take some advanced structural analysis and engine courses? Structural analysis, some CFD and engine control courses. Yeah, absolutely. Yeah, simulations. I mean, if you become good at that, like, that's good. That's really good. and control courses. Yeah, for sure. Just Google programming with Mosh. Like it's the first one. You type in Python tutorial on YouTube, and you'll see one that has like 16 or 17 million views. That's the one that I've been yeah. No, it's not. That's not the thermal software. NASA created this software that's used for engine modeling. I could probably say it, but I don't really. I'd rather not, just for work and stuff. But hmm you want to go through that integral again? It's already gone, man. Hey, Len, how's it going, man? Thanks for stopping in. What's the best language to learn for someone starting? Yeah, man, learn Python. Would your job subsidize programming courses for you? Uh yeah, that's a good question. That's a good question. I should find that out. I mean, I paid for the Brilliant. That's a good question. I'll have to find that out. They probably will, yeah. As a student, I'll be using CAD software. Of course, yeah, you'll definitely be using CAD software. Should I get a computer? Yeah, you should get a laptop that can handle probably minimum, probably SolidWorks, since you're probably going to learn SolidWorks. You don't have to worry about that until you start taking it. You can figure out exactly what you need. But yeah, you do need a laptop that has the power to run these to run some of these packages. So probably be at least 32 gigs and 32 gigs of RAM and 4 cores and yeah, something like that. Do you know of any classmates or colleagues that have gone into motorsports? No, I don't. I'm gonna start making next year, and Formula One would be my goal. Oh, that's pretty cool, man. Yeah, I mean, definitely join your clubs. That's probably the biggest the biggest thing you should do. Your school probably has like a Formula what do you call it, SAE club or like yeah. Make sure that your university has those clubs because that's pretty big. Do I have a life other than engineering? Yeah, I mean, I'm doing this. It depends, right? It's really you get some jobs where you work a lot, and you get like the jobs I've had have been pretty good work life balance. I think the school's a lot more intense than work, but that's what I'd say. I mean, what company did I work? You just look up my LinkedIn. Any tip for an aerospace engineering undergrad to go to start in September? Yeah, just make sure that you focus on like getting internships, join some engineering clubs. Yeah, kind of talked about that before. I play any video games? No, I don't. I used to. Alireza. Thanks, man. I miss you too. Okay. A couple more and then we'll bounce. What I think about Inventor, I've never used Inventor, so I wouldn't know. It's a pretty common one though. A valuable safety knowledge, yeah, man. Yeah, I'm learning that it is pretty valuable. It is very valuable. I don't upload, like, I'm not really a frequent uploader. I like to take my time on videos just because, I mean, I don't know. Because here's the thing, if I upload more frequently, the videos won't be as, I don't know. Yeah. I don't like to do sort of quick 4 or 5 minute videos twice a week. I'd rather do longer videos that may take a little bit more time. So like this math one, the reason why I haven't started it is because I've been doing research. It's like if I'm gonna explain like how math is used, I need to learn how math is used myself because it's not totally intuitive to me. Just like with the software one, right? I spent probably a week like researching what the best softwares are to learn and how they're all used. And then I'll film it and then I'll release it. So like, yeah, sometimes it takes, 3 weeks or even a month. It's not that I'm not doing it. I mean, I was traveling. I did travel this week, so I haven't done anything for the videos, but yeah. I don't know, we'll see. Maybe I'll upload more frequently. But I always like to take a little bit more time with the video itself and then make it a bit longer. And I don't know, it seems to be working. But how do you reach out to a recruiter that doesn't sound like you're begging for a job? So you always want to, okay, a few things. You want to show that you've done your homework. Okay, so you want to know some things about the company. So like that's probably the biggest thing. A recruiter or an employer, they don't want to feel like you're sending the same script out to everyone, right? You're like you said, you don't want to come across like you're desperate. You're just shooting like whichever one sticks, right? Like you want to be persistent, but not begging. So how do I explain this? So if let's say like, I'm calling an employer and hey, my name is blah blah blah. I'm a second year student. I was just looking through your co-op position, your company. I'm really interested in what you guys are doing. I feel like I may not be the most experienced, but I think I can add a lot of value because blah 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 blah. Because I'm good at blah 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 blah. Do you have a few minutes to talk? I'd love for you to learn more about me and see how I can add value. Like that should kind of be the mindset. So a couple of times we get calls at work, and the guys, and like God, like that's good. You want to be like calling. You want to be calling these people, right? Or you want to be DMing people on LinkedIn that work at a company that you want to work for, right? Whatever. And that's kind of how you want to come across. And actually learn about the company, right? Really learn about the company and what their mission is and how you can sort of add value. So that's kind of the mindset that you want to have. You don't want to be like, hey, I'd love to work with you guys. I really love rockets. Like I got a couple calls like that. I'm like, it's not about what you want. It's about how what we want. How can you help us, right? So, but yeah, you can just reach out to people and like, just be honest with them. Like, just be honest. Like, I'm not super experienced, but like I work hard and just I really like what you guys are doing. I think it's fascinating and blah 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 blah. develop like little relationships, and you might not get something right away, but at least you'll develop that relationship. You can add them on LinkedIn. You can, whatever. For the dissertation, the project for dissertation, yeah, I don't know. CFD is pretty important, man. CFD is pretty important. I need to get good at it myself. Like, yeah. Is electrical or aeronautical the future of engineering? Well, they kind of like electrical is not really an industry, right? It's like every industry uses electrical. Electrical is a really good one to go into. Probably the best one to go into. The best major. Have I had people in my comedy who came from physics? No. And I get this question too, and I'm not quite sure how to answer it as far as like okay, I have a physics degree. Can I go into engineer? Can I become an engineer? I think you need to take. You might convert some of your courses. You probably take some engineering, or you get credit for some of the engineering. But hey, Elon did it. So Elon has his physics degree, and he basically self-taught and became a self-taught engineer. So it's possible. In engineering, is theory more important or practical? Practical, man. Practical. The theory is something you can always relearn. You're never going to be doing. I shouldn't say never, but most of the time, you're not going to do problems as difficult as you are in school. It's more the practical. Like, this is why I tell you guys, get internships, right? Get internships. That's what employers care about, and that's what they care about is the practical experience. Yeah, I take EE over Mechie right now. Coming in Canada, can we study? Can we collab? What do you mean collab? Industrial engineering. Yeah, I don't know much about industrial, but it seems like from what I've heard, from what people are saying, it seems like a pretty growing one. I don't know how many schools recognize it, but yeah, you'll learn more about it. Industrial is kind of the one that's not design based, right? Most of them are design based, and industrial is more management and business side of things. Anyway, get on the stream there, guys. So thanks for tuning in. We'll do these tutorials. Yeah, I don't know. I kind of like doing. I don't know. Let me know what you guys think of the tutorials and stuff. Maybe we'll do some that's Python or 3D modeling, whatever. But yeah, okay, I can do a video on my senior project, sure. Yeah. So, thank you all for tuning in. We'll see you guys soon. All right. See you later. I'm gonna put this stream in the Discord. So if you're not signing into the Discord, y'all can log in there, and then if you guys want to watch it later, you can do that. So peace out, guys.